today's lecture on transportation problem. And here in the problem it is said that solve the following transportation problem to maximize the profit. Okay, so this is very important word for transportation problem. Transportation problem generally in minimizing type. Okay, but it is said that this is maximize the profit. That is, this type of transportation problem is said to be maximization type of transportation problem. Maximization transportation problem. Okay, and to solve the maximization transportation problem, we must have to convert it into minimization type transportation problem. How to convert it to maximization to minimization? To convert it into minimization type, we first subtract all the cost coefficient in each corresponding cell from the maximum cost of the table. And so we have to first find out the maximum cost coefficient of the table. And clearly the cost coefficient are 40, 25, 22, 33 and etc. Clearly we find that 44 is the most cost or maximum cost of the table. Okay, so to convert it into minimization type, we first subtract all the cost coefficient from 44 and write it into the corresponding cell. Okay, so minimizing transportation problem becomes by subtracting corresponding cost from maximum cost, that is 45. Okay, and the minimization type of problem can be written in the table as, the table is same type. There are 3 row and 4 column as given as above. Okay, and we subtract 40 from 44 because 44 is the maximum cost, so we get here 4. We subtract 44 from 44, so we get here 0. We subtract 38 from 44, so we get 6, and we write all the cost in similar manner. And as above, we write all the capacity AI and all the demand BJ. Okay, so we get a new transportation table, that is the transportation table of minimization type. Right, now we first check it is balanced or not. Okay, to check it, we first find out the value of summation AI. This is given by 100, 30 and 70. The sum of 100 plus 30 plus 70, this is 200. And summation BJ, this is given by 40, 20, 40 plus 20 plus 60 plus 30, 60 plus 30. And clearly this is 60 plus 60 plus 30, so this is 150. Okay, and it is shown that summation AI, this is greater than summation BJ. So this problem is unbalanced transportation problem. Okay, so there is a one exception, this is maximization type, and also this is unbalanced, so it is unbalanced. Unbalanced transportation problem. Okay, now to convert it into balanced one, we must add a dummy destination with demand summation ai minus bj, that is with demand 200 minus 150, that is 50 unit of demand. Okay, so we add a dummy means fictitious, okay, that is artificial. Dummy destination, we name it is S because X, Y, Z, T, and S we say dummy destination with demand summation ai minus summation bj, that is 200 minus 150, so demand 50 unit. Okay, now we form a new table with column number 5, and in the dummy column, that is in the column S, we take all the cost coefficient is equal to 0. Okay, so the new table, that is the balanced transportation table, looks like that. This is with 5 column, 4 column and 5 column, and row are again 3, and here destination are X, Y, Z, T, and S we say here, and this is A, B, C, and the demand are 40, this is 20, this is 60, this is 30, and this is 50. This is the fictitious demand, and the capacity are 100, this is 30, this is 70. Okay, and we say that the cost of this column are 0, and the cost of other column or other matrix are as shown in the previous table. So this is 4, 19, 22, 11, and this is 0, this is 9, this is 14, this is also 14, this is 6, 16, and 11. Okay, now we use to find the initial basic feasible solution of this problem. We use the method VAM. Okay, that is we use Vogel approximation method. Now to use Vogel approximation method, we have to first find the each row and each column's penalty. How to find out the penalties? To find out the penalties of first row, we find out the least cost and the next minimum cost. Here the least cost is 0 and next minimum cost is 4. So the difference between 0 and 4, this is 4 and this is the penalty. We write it in a bracket. Okay, and similarly the least cost is 0 and again next least cost is also 0. So the penalty is 0. And here this is 0 and next is 6. So the penalty is 6. Similarly, the penalty for this column is 0. Penalty for this column is also 0 because 11 and 11. Penalty of this column is 2 because 14 and 16. Penalties of this column is 3 because 6 and 9. And penalties of this column is also 4 because 0 and 4. Okay. Now we find out the maximum penalty. Here 6 is the maximum penalty. Okay. So we try to allocate in this row, that is the penalties on the corresponding row or column where the maximum. Okay, and it is says that in this row 0 is the minimum cost because 0 is the minimum cost here. So we try to allocate maximum amount in this cell. Here capacity is 70 but demand is 50. So we allocate 50 unit in this cell, right? And then we get the next iteration by taking 20 unit, here 30 unit, here 100 unit. This column is exhausted, so this column may be crossed out. Okay, and this is 30, this is 60, this is 20, this is 40. Again we calculate the penalties. Clearly the penalties of this column are unchanged because there is no change in the cell, okay, of this column and also this column. So we write here directly the above penalties. This is 3, this is 2, this is 0. But the penalties of these 3 rows may be changed because the cell in each row are crossed off. And now the penalties are list cost is 4 and the next is 11. Okay, so the penalties is 7, list is 0, next is 9. So the penalty is 9, list is 6 and next list is 6 also. So this is 0. And clearly 9 is the greatest penalty. So we allocate maximum amount in the minimum cell cost in this row, that is the second row. And clearly this is the minimum cost row, minimum cost cell. So we allocate here 30 unit because here capacity is 30, demand is 40. So here we allocate 30. Okay, and next iteration gives the result as here 10 unit remain. This is cross off. Here we write cross off sign. Here we also write cross off sign. And this row may be cross off from the table. Okay, and again this is 100. This is 20. This is 30. This is 60. This is 20. Okay. Now the penalty of this row is unchanged. Here we write 7 and also here we write 0. But penalty of this column and this column may be changed. The penalty is 4 and 6, so this is 2. This is 6 and 19, this is 30. This is 22 and 16, so this is 6. And this is 11 and 11, this is 0. Okay. And if we carefully in each iteration, it is checked that the total capacity, that is 120, this is 120, and total demand here, this is 60, 20, 10 and 30, this is also 120. So our problem from this stage, we say that it is correct. Okay. Now here the maximum penalty is 30, so we allocate here, that is in the second column. Here minimum cost cell is 19 of 6 is the minimum, so we here allocate 20 unit because this is demand is 20 and capacity is 20, so we put here 20 unit. Okay, and there be also a exceptional case arise because row and column together cross up because demand is fulfilled and capacity is also exhausted here. So we make an exceptional operation here. We see carefully here. If row and column together cross up, then any one of this side, either row or column, we first cross up. Okay, here we let the column be crossed off. Okay, now if we cross off again the row in this iteration, then the number of allocating cell must be less than m plus n minus 1. So this is not basic feasible. Okay, there be a degeneracy in this transportation table. Okay, so we put here in any cell of this row and small amount, and this is we take epsilon. Okay, this is a small amount, we say this is epsilon, and if we put this epsilon amount, this is very small tending to 0, this this allocation has no existence practically. In the minimum cell or minimum cost cell of this row, here minimum cost cell is 6, 16 and 11, so this is 6. Here we allocate epsilon amount, okay, to get or to remove the degeneracy of transportation problem. And we write here epsilon greater than 0 such that xij plus minus epsilon, this is equal to again xij. Okay, so it is clear that epsilon have no physical importance. To solve or to remove the degeneracy, we put here epsilon amount, and then the remaining row cross out. Okay. Now it is clear that in the next table there be only one row with capacity 100 unit, and also 3 polymer remains, capacity 10, 60 and 30, that is 100. So there will be no option to calculate any type of penalty or other. So we put directly here 30 unit, okay, here 60 unit and here 10 unit. And so the total demand is fulfilled and total capacity exhausted. So we get initial feasible solution by using Vogel approximation method, and it is clear that number of basic cell or allocating cell is 1, 2, 3, 4, 5, 6, 7. Okay, so basic cell or allocating cell is, this is 3, 4, 5, 6, 7, and we write 7 as 3, this is n, plus this is 1, 2, 3, 4, 5, this is 5 minus 1, that is m plus n minus 1. Okay, and we write, so obtain solution is basic feasible solution of the transportation problem. Okay, so we get initial basic feasible solution of the transportation problem by using Vogel approximation method. Now our remaining work is to determine this solution is optimal or not. Okay, to test the optimality of this solution, we see the video of second part, that is the part B. Okay, thank you for watching.